It is given the next information. This question asks you to explore the behavior of some key features of the function fn of x is equal to x to the power n multiplied by a minus x to the power of n, where a is positive real and n is a positive integer. In parts A and B, only consider the case where a is 2. Consider f1 of x is x multiplied by 2 minus x. A, sketch the graph. Y is f1 of x, so we need to plot this graph, stating the values of any axis intercepts and the coordinates of any local maximum or minimum points. 3 marks. So it's quite easy. We need just plot a graph over this function, and we can see it's a usual parabola, and we can see that roots are 0 and 2, and we know that there is a maximum in the middle, maximum because it's a concave down parabola, because negative x squared. So roots are 0, 2. At x is 1, there is a maximum point, and substituting 1 for x, we get 1 multiplied by 2 minus 1 is 1. So 1, it's a y coordinate of a maximum point. And that's all for this question. Next, consider fn of x is x to the power of n a minus x to the power of n, where n is positive integer and n is greater than 1. B, use your graphic display calculator to explore the graph of y is fn of x for odd values, n is 3 and n is 5. And the even values, n is 2 and n is 4. Hence, copy and complete the following table. So we need a number of local maximum points, number of local minimum points, and number of points of inflection with 0 gradient. Inflection with 0 gradient. So use a calculator. Y is, and we consider a given function x to the power of n a minus x to the power of n, and it is given for a and b. A is 2, so we consider a to be equal to 2, and for n is 3, we get x cubed multiplied by 2 minus x cubed, and a window graph, and we can see that there is only one maximum point and 2 points of inflection with 0 gradient at this point and this point. And for n is 5, and actually you can guess, since it's the same row, it should be the same. Yes, and we can see that it's similar. So maximum point, there is only one maximum point, no minimum points, and 2 points of inflection with 0 gradient. And now let's consider n is 2. So x squared, 2 minus x squared, and we can see that there are 2 points of minimum and 1 point of maximum, and there are no points of inflection. So it's 1 maximum, 2 minimum, and 0 points of inflection. You may check for n is 4, and it will be the same. The next. Now consider fn of x is x to the power of n a minus x to the power of n, where a is positive real, n is positive integer, n is greater than 1. C shows that derivative of a given function is equal to. So we need to find the derivative, and the answer is given 5 marks, and for previous it was 6 marks. So let's find the derivative. It's quite easy. We can see a product, so we just use the product rule. So derivative of f of x to the power of n, it's n x to n minus 1, and multiplied by just the second function, a minus x to the power of n, plus the first function, x to the power of n, multiplied by the derivative of the second, so it's a minus x to the power of n minus 1, but it's some complicated function to the power of n, so we apply chain rule, and chain rule says that it's a function and it's n function to the power n minus 1, and multiplied by the function, it's a minus x derivative, so negative 1 also arises. And we can see that we can factor out n x to the power of n minus 1 and a minus x to the power of n minus 1 multiplied by it's a minus x minus x. Or we can see that it's just a minus 2x. And it is equal as required, nx to the power of n minus 1, a minus 2x, and a minus x to the power of n minus 1. Yes, it's correct. The next, D. State the 3 solutions for the equation f and derivative of x is equal to 0. So it becomes n x to n minus 1, a minus x to the power of n minus 1 multiplied by a minus 2x is 0, and we can see that x is 0. From here, x is a over 2, and x is a, this a minus x, to be equal to 0. And notice that these are stationary points, and we will need them for next questions. So it was 2 marks. E shows that the point a over 2 and the corresponding y coordinate fn of a over 2 on the graph of y is fn of x is always above the horizontal axis. 3 marks. So let's consider x to be a over 2, and we need a function fn. It's this, the general form, and just substitute a over 2 for x. So y for fn of a over 2 becomes a over 2 to the power of n, a minus a over 2 to the power of n, and hence it's a over 2 to the power of n, a over 2 to the power of n, so it becomes a over 2 to the power of 2n. And since a is real and positive value raised to positive or negative power, it doesn't matter, it's always positive. So it's not required that n is greater than 1, but also in general to n it's even power. Any value raised to even power, it's positive, but it's not necessary here because a is positive, hence positive to any power. It doesn't matter, even power is negative, it will be like this or like this. So a function x to the power of some value raised to the power of x, it's always positive. For x is positive or negative, it doesn't matter. So since a is real and positive, a over 2 to the power of 2n is greater than 0. And hence y coordinate and the question is of the graph, and hence y is fn of x is always, hence always above the horizontal axis. Okay, the next f, hence otherwise shows that derivative of fn at a over 4 is greater than 0 for n is positive integer. So where is the derivative? It's this expression, and we just consider derivative at a over 4, and it becomes n a over 4 to the power of n minus 1, a minus a over 4 to the power of n minus 1, and multiplied by a minus 2x. So a minus 2 multiplied by a over 4, so it's a over 2, and it becomes n a over 4 to the power n minus 1, 3a over 4 to the power n minus 1, and a over 2. So since a is real positive, there is the product of 3 positive factors. Hence f and derivative at a over 4 is greater than 0 as required. It was 2 marks. G. By using the result from part F and considering the sign of f and derivative at -1, shows that the point 0, 0, or about origin, on the graph y is fn of x, is I, a local minimum for even values of n, where n is greater than 0 and a is positive real. 3 marks. So we need to consider n. If n is even, let's consider f and derivative at -1. What is fn derivative? Is this expression, so it's n -1 to the power of n minus 1 multiplied by a minus x, so it's a minus -1, so a plus 1 to the power of n minus 1, and multiplied by a minus 2x, so it's a plus 2, and a is real and positive, and if n is even, we get that it becomes n -1 to even minus 1, it becomes odd, or we can write that -1 to the power n minus 1 is equal to -1 to odd power is less than 0, and a plus 1 to n minus 1, and actually it's positive, and a plus 2 is also positive, and actually it's not necessarily required n to be greater than -1. Even if power is negative, some number raised to negative power, it will be also positive, and hence derivative at -1 is negative. And from the previous, from f derivative at a over 4 is positive, and we remember that there are 3 stationary points: origin a over 2, and a over 4 is to the right from origin, but to the left from this next stationary point. So -1 is to the left, and a over 4 is to the right from origin, and hence we can conclude that since x is 0 is a stationary point, and derivative at -1 is less than 0, and derivative to the right is greater than 0, as derivative changes sign from negative to positive. Therefore at x is 0, or point, therefore x is 0 is minimum as required. A local is, therefore is a local minimum. The next, it's the same question. By using the result from part F and considering the sign of derivative at -1 shows that the point 0, 0 on the graph of y is fn of x is, and the next part, a point of inflection with 0 gradient for odd values, so where n is greater than 1 and a is positive real. 2 marks. For previous it was 3 marks. So now n is odd, and and it means the next that derivative at -1 becomes, we can see it's the previous result, then it becomes -1, or let me write, it becomes n -1 to n minus 1, a plus 1 to n minus 1, and a plus 2, and -1 to n minus 1, it becomes -1 to even power, and hence it's positive, and also a plus 1 is positive, and also to the power of n minus 1, and a plus 2 is positive, hence derivative at -1 is positive, and also derivative at a over 4 is also positive, it's from f, and therefore we can see that, and at x is 0 there is a stationary point, and the function is increasing because derivative is greater than 0, is increasing to the left and to the right, and since at x is there is a stationary point, it means that there is horizontal or zero gradient, so zero gradient, and hence we get the required result. Therefore 0, 0 is a point of inflection with zero gradient as required. The next, consider the graph y is x to the power of n, a minus x to the power n minus k, where n is positive integer, a is real and positive, k is real, h states the conditions of n and k such that the equation x to the power of n, a minus x to the power n is k, has 4 solutions for x, 5 marks. And we can see that y is k, it's just a horizontal line, and we know that points or intersection of two graphs, when we plot the left hand side and the right hand side functions, points of intersection are roots, and we need four solutions, 4 roots, and to get 4 roots it must look like this. Y is k, and we can see 1, 2, 3, 4 points of intersection, hence 4 roots. So there must be 1 maximum and 2 minimum points. And to get, and since stationary points are 0, a over 2 and a, it's from this result. Hence the first point must be minimum, then maximum, and then again minimum. And since we need at x is 0 at origin to be minimum, and from this question G, n we can see that n must be even, so the derivative changes sign from negative to positive, hence at origin there will be minimum, so n is even. Otherwise the function will be always increasing about the origin, and this point at x is 0, it's a point of inflection, but we cannot get 4 roots at all, so it must be like this. And to find a possible range of values for k, we need y coordinates of these minima and this maximum point. And we consider just this function x to the power of n, a minus x to the power of n, and at x is 0, we can see that it's 0, so it's 0, 0, or y coordinate is 0, and y at a over 2 becomes a over 2 to the power of n, a minus a over 2 is a over 2 to the power of n, and it's 8 over 2 to the power of 2n, and y at a, we can see that it's just 0, and hence we can plot this graph more accurately, and it looks like this. So it's fn of x, it's 0, a over 2 a, and this value is y coordinate is a over 2 to the power of 2n, and hence we can see that when k is greater, it must be strictly greater, because if it is equal to 0, we can see that there will be only 2 points of intersection, but we need 4, so k must be greater than 0 and less, and also strictly less, because if k is equal to a over 2 to the power of 2n, we can see there will be 1, 2, 3 points of intersection, but we need 4, and k must be less than a over 2 to the power of 2n to get 4 roots as required. And that's all for this question.